Okay, hello everybody. Um, let's try to finish up this chapter. So let's see here. I think we're here. Sometimes the same type of thing need different types of data. All right. So we're gonna move on from structs and on to something slightly different. Um, let's read. Sometimes the same type of thing needs different types of data. Structs enable you to model more complex things from the real world. But there are pieces of data that don't have a single data type. For example, take the sale today. We have 6 apples, 1.5 pound of strawberries, and half pint of orange juice. All of these actually describe a quantity. We have an integer and 2 floating points. So if you want to record, let's say, a quantity of something, and that quantity might be a count, a weight, or a volume, how would you do that? Well, you could create several fields with a struct like this. So we can create the integer count, the float weight, the float volume, and model it as a fruit struct. But there are a few reasons why this is not a good idea. First, it will take up more space in memory. So basically, what they're trying to say, let me back up a little bit, but this problem is trying to describe that, okay, I want to have a quantity of something, right? A quantity of something, meaning that not every one of these fields are chosen. You only choose one. It could be in one instance you could have a container that shows a quantity that is a count, or in another instance you want to use a weight to signify quantity, or another instance a volume, right? And we want to model that as fruit, like the weight of a fruit, for example. But we only want to use one of those three, and we can model it in a struct, but then it will take up more space in memory because these have to be allocated. Every time you create a struct, right, you have 2 bytes for the short, you have 4 bytes for the weight, and you have 4 bytes for the volume. And also, it's error prone because someone might set more than one value, and there is nothing called quantity. So, like, it's really hard. Like, if we wanted something called quantity here, we would have to like add that in too. So it would be really useful if you could specify something called quantity in a data type and then decide for each particular piece of data whether or not you're going to record a count, a weight, or a volume against it. So basically one out of the three, right? So we need a different way to model this type of behavior or data. And in C, you can do that just by using a union. So a union is sort of like a struct, but not really a struct. So let's go deeper into that. So every time you create an instance of a struct, the computer will lay out the fields in memory, one after another. So this is what a struct looks like, okay? So, every time we create a struct, we allocate this many things, these this many bytes, right, of memory. A union is different. A union will use a space for just one of the fields in its definition. So if you have a union called quantity with fields called count, weight, and volume, the computer will give the union just enough space for the largest field and leave it up to you which value you will store in there. Whether you set the count, weight, or volume field, the data will go into the same space in memory. So in this case, quantity here is just enough, like just taking the biggest sized field and allocating that amount of memory, and it could be either a short or a float in this case. So if a float takes 4 bytes long and a short takes 2 bytes long, then actually this union is going to be 4 bytes because it needs to still be able to hold the biggest thing, right? And yeah, you definitely declare a union kind of like a struct, except for instead of using the struct keyword, you use union. And each of these fields will be stored in the same space, okay? And these are all different types, or they're different quantities. All right, so let's just sort of model that real quick. So in like our normal thinking of structs, for example, uh, whoops, in our normal thinking of structs, if we have, let's say, why I can't draw today? Let me just, what? Okay, close enough. Okay, so we have something like a struct. We have, what do we have? Count, right? Short. We have float, weight. Then we have float. Is it volume? Something like this, right? If this is 2 bytes, this is 4 bytes, and this is 4 bytes, when we allocate a struct, it's going to be like this. 2 bytes to go for the count, 4 bytes go for the weight, 2, 3, 4, and then 4 bytes go for the volume. So how we model that is 2 bytes for the count, and then we have 4 bytes for the weight, then we have 4 more bytes for the volume, and then the total of this would actually be 10 bytes. Okay? Union is going to be different. A union means that, okay, I only want to store one of, these types of fields. So it looks more like this. I think we had short count. We had float weight. And we have float, volume. Okay. And then we have our union here, our memory to represent our union. This is 2 bytes, this is 4 bytes, and this is 4 bytes, right? So what we want to do is we only want to be able to select one of these. Well, if that's the case, then we just need to represent our union in memory by the maximum, either float or volume, size, in that we can represent that type of property. So in this case, it's 4. Okay. So we have 4 bytes to represent the union that models quantity. In this case, if we wanted to store count, we would just occupy 2 bytes of the 4 bytes. If we wanted to store something like weight, we would occupy 4 out of 4 bytes. And we want to store volume, we'll occupy 4 out of 4 bytes. All right, so we're only limited to storing one of these types of quantities in this case. And then how you actually read them is it's interpreted, right? So let's say you stored, for example, weight, right? So you store weight, and that took 4 bytes. Now, when you read the union, for example, you would read it as something like Q weight, right? Oh, my pen again. Okay, and that'll get you back whatever the window is here. So that's 4 bytes. But what ends up happening is that, let's say you did store weight, but then you decided to access it as count. What ends up happening now is that then you would actually inadvertently, most likely, read 2 out of those 4 bytes instead. So nothing is stopping you from reading count if you store it as weight. All right. So, you've occupied the 4 bytes, but it's up to you still to sort of determine how you want to interpret it when you're using union. So, yeah. So how do you use a union? When you declare a union variable, there are a few ways of setting its value. C89 style for the first field. If the union is going to store a value for the first field, then you can use C89 notation to give the union a value for its first field. Just wrap the value in braces. So this, by default, if you declare a union, not declare, if you create a union, right, without any labels, just giving the first value, it's going to take that first field as a default. It will assign it to the first field. So in this case, if we had this quantity union here, by not providing exactly what property is going to be assigned to, we automatically assume count. Okay? So designated initializers set other values. A designated initializer sets a union field by name like this. So you can't specify the exact property you want to assign to. So you just use this dot notation here. So curly brace, dot, the property you want, and it equals the value. Okay? Or you can do it after the fact. So you create a union, which will initialize everything to 0, and then you can just do q.volume 3.7. Okay? But the one thing to remember, whichever way you set the union's value, there will only ever be one piece of data stored. The union just gives you a way of creating a variable that supports several different data types. So you can mix different data types to represent one, I guess, one conceptual thing, right? In this case, quantity. So there are no dumb questions. Why is a union always set to the size of the largest field? Well, the computer needs to make sure that a union is always the same size. The only way it can do that is by making sure it is large enough to contain any of the fields. Why does the C89 notation only set the first field? Why not set it to the first float if I pass it a float value? Well, to avoid ambiguity, if you had, say, a float and a double field, should the computer store 2.1 as a float or 2.1 as a double? By always storing the value in the first field, you know exactly how the data will be initialized. Okay? Okay. Sure. Okay. Well, those designated initializers look like they could be useful for structs as well. I wonder if I can use them there. So yes, you can use designated initializers in structs. They can be very useful if you have a struct that contains a large number of fields and you initially want to set a few of them. It's also a good way of making your code more readable. So something like this in structs. So we took our structs program again, okay? I think at some point, yeah, we created Myrtle. We could do something like this. Dot name equals, I like to have spaces, dot species equals, and then finally dot age equals. So we could definitely initialize structs like this. Unions are often used for structs. Once you've created a union, you've created a new data type. That means you can use its values anywhere you would use another data type like an int or a struct. For example, you can combine them with other structs. So notice how we have the union quantity, right? So here we have a struct that actually makes use of that union. So we could do amount.count, amount.weight, or amount.volume, for instance. So, and you can access the variables in the struct and union combination using the dot or arrow notation you used before. And we could assign it like this too. So that's a useful way to do nested, right? Nested assignment. So if we were to go back to, let's say, structs test 2, this is, even though this is a union, I think we could do that with structs too. So we had this crazy thing here that we created, this fish struct. We could do something like name, okay? Then we could do something like species, And then we could do something like, what is it? Dot T. Okay. We could do dot age. And then here we could do something like dot care dot food dot ingredients dot care dot food dot weight. Then we do dot care dot exercise dot description. Then finally dot care dot exercise dot duration. And this would actually work too, I think. So let's try it. Yeah, so it works the same way, right? And we can even take it to another level. So like this works right here. Yep. Take it to another level, I guess, if we did something like maybe if this is too much, we could do something like dot care equals dot food equals dot ingredients. Okay. We could do it this way too. I think it works the same way. There we can just delete this. Okay, so that looks a little cleaner, right? And then same thing. So we can be very flexible with the way we want to represent the struct, but this is the most powerful thing here, the designated initializer. It makes things way more readable, I think. So that's great. Yeah. So yeah, and you can kind of combine like unions and structs together, and it'll be all good. So okay. So mixed up mixers. Okay, let's do it. It's margarita night at the Head First Lounge, but after one too many samples, it looks like the guys have mixed up their recipes. See if you can find the matching code fragments for the different margarita mixes. Here are the basic ingredients. So we have a union. Okay, union. That means only one of these, either of these can be populated. And then we have a struct that will have three properties, but I think only one union here and two floats. So here are the different margaritas. All right, so we have a margarita that has 2 tequila, 1 Cointreau, and then lemon lime. Okay, so the citrus type. Since there's no designated initializer here, by default it gets to be a lemon. Okay. Then we have a margarita that is 2.0 tequila, 1.0 Cointreau, and then citrus dot lemon. So that's easy. Citrus dot lemon is 2. Then we have a margarita here. Huh. Interesting way to do it. Is that even right? Maybe. Probably not. Okay. Then we have 2. Okay. 1 Cointreau. And then we have lime pieces now in our union to be 1. Okay. And this one here is a tricky one, right? It's again 2 tequila, 1 Cointreau, and then I think this one is just going to go to lemon. Because there's no designated initializer. Same thing for this one too. So it would just be 2 goes to lemon. But I'm curious about this one. This one is something I've never seen before because it's just like 0.5. C. Huh. Okay. And finally, here are the different mixes and drink recipes. Which of the margaritas need to be added to those pieces of code to generate the correct recipes? So 2.0. So that's easy, right? So we just did all of this. But I'm curious about the 0.5. Oh, one of these pieces of code compiles, the other doesn't. So it's going to be what? Wait, what? Wait, which of the margaritas need to be added to these pieces of code to generate the correct recipe? Oh, so we have all these and we have to match it. Okay, okay, cool. So, sure. So 2 measures of tequila, 1 measure of Cointreau, 2 measures of juice. So juice will be probably lemon here instead of lime pieces, right? So one of these two are good. Oh, hey. Huh. So one of these two, right? No, no. Wait, lemon? Okay. Lemon. Yeah, one of these two, right? And then this one is half measures of juice. So it's going to be this one. Okay. And this one is going to be 1 piece of lime. So that's going to be this one. Okay. And then, what is this? I just don't get it. Wait, is this a float lemon? Yeah. I just don't get it. Okay. Margarita M2, 1, and then a union, 0.5. Margarita M equals this. Margarita M. That's a struct. This is a struct. But why doesn't this? I guess one of these will compile. Okay, well, let's figure it out. Huh. So none of these lines were used. Okay, so this one's the one I wasn't sure about. They didn't use that one. So I don't get it. This one would still be the same thing though. Huh. Okay, but yeah, we got mostly everything right. And this one compiles perfectly. It's just one of the drinks above. This one doesn't compile because the compiler will only know that 210.5 represents a struct if it's used on the same line that a struct is declared. When it's on a separate line, the compiler thinks it's an array. Whoa, really? We can only declare structs like this. Is that true? Wow. Wow. Okay, so if you actually initialize the struct declaration afterwards, then it's going to be interpreted like an array. That actually might be a good point because it's hard to tell. Hmm. Anyway, hey, wait a minute. You're setting all these different values with all these different types and you're storing them in the same place in memory. How do I know if I stored a float in there once I've stored it? What's stopping me from reading as a short or something? Hello? Yeah. See, this is why that's what I made the point earlier is that it's up to you to interpret it, right? So, like, going back to this example, if you decide to store some, like this union, you decide to store weight using 4 bytes in one instance, but then you read it as count in another, you know, I don't think there's anything stopping you, right? So, the response here is that's a really good point. You can store lots of possible values in a union, but you have no way of knowing what type it was once it's stored. The compiler won't be able to keep track of the fields that are set and read in a union. So there's nothing to stop us from setting one field and reading another, right? Is that a problem? Sometimes it can be a big problem. Yeah. So if we were to do cupcake order, so this union called order that is of a cupcake union type, if we say 2, since there's no designated initializer, it'll be weight. Okay, 2 will go into weight, but then now we say that, well, we're accessing the count now. So since count is an int, 4 bytes, it'll be interpreted, that 2.0, that float number, is going to be interpreted as an int, which gets us this number here. So yeah, it did bad things. So you need some way of keeping track of the values we stored in a union. One trick that some C coders use is to create an enum. Let's see. An enum variable stores a symbol. Sometimes you don't want to store a number or a piece of text. Instead, you want to store something from a list of symbols. If you want to record a day of the week, you only want to store Monday, Tuesday, Wednesday, etc. You don't even need to store the text because there are only going to be 7 different values to choose from. That's why enums were invented. Enums lets you create a list of symbols like this, okay? So it'll be like red, green, what's puce? So those are like the constants kind of, but they represent like they're like kind of like a label. So any variable that is defined with the type enum colors can only be set to one of the keywords in the list. So one of the 3 only. So you might define an enum colors variable like this. So the favorite color from enum colors is puce. Okay. Under the covers, the computer will just assign numbers to each of the symbols in your list. So this will be like 0, 1, 2. Okay. But you don't need to worry about what the numbers are. Your C code can just refer to them as the symbols. They'll make your code easier to read, and it will prevent storing values like REB or PUSE. I see. So you can't do PUSE because it's not part of this enum colors enumeration here. Only these 3 are valid. Okay, so how does this relate to unions? Let's see. Well, let's see. Okay, so we have an enum called units of measure. This is the way we define an enum, type def enum, with the, I guess, possible labels as unit of measure. We have a union here that represents quantity, as always. But then we have a struct that has not only the quantity I see now as a union property, but also the units of measure, enum. So I'm guessing based off of what value this is stored in, we interpret this union based on that, right? So in this case, if the order, which is a fruit order dot units equals pints, then we do order dot amount dot volume. Okay, then we do else if what is it, units dot, I guess, weight equals pounds here, then we say the order weight. And the same thing for here. It's like else it'll be the let's see, order dot amount dot, so order dot amount dot count otherwise. Okay, and here is going to be the enum we assigned that right here, which is going to be, let's see, is this count? This will be count, so it's going to be this enum count, and then this is enum pound, so this has to be weight, and this one is volume, so it has to be volume for the enum right here, right there. So the answer, see, order units pints. So based off of whatever this struct has as the enum value of units, right, it tells us to then read it as volume. For example, this is pints. So you're keeping track by manually setting that label so that you can refer back to later. It's going, hey, what did I set this to be so that I can know how to read the union, right? So I think that's the gist of it. Okay. All right. Overheard at Head First Lounge Union. So I said to the code, hey, look, I don't care you gave me a float or not. You asked for an int. You got an int. Dude, that was totally uncalled for. That's what I said. It's totally uncalled for. Struck says, everyone knows you only have one storage location. Union goes, exactly. Everything is one. I'm like Zen that way. Enum. Huh? Enum. What happened, dude? Shut up, Enum. I mean, the guy was crossing the line. I mean, if he had just left the record, said, I stored this as an int. Okay, Union goes, I mean, okay, so here's what they're saying. Union is everything like is wrapped up as one thing. Um, but Union goes, I mean, if he had just left a record, so like if he had just left me something to tell, I stored this as an int or things like that. It just needed an enum or something, and then enum goes, you want me to do what? And Struck goes, shut up, enum. And Union goes, I mean, if he wanted to store several things at once, he should have just called you, am I right? Which is a struct. Struck goes, order. That's what these people don't grasp. Enum goes, ordering what? Struck goes, separation and sequencing. I keep several things alongside each other, all at the same time, dude. Union goes, that's my point. Struck goes, all at the same time. All. Stress on all. Enum goes, so has there been a problem? Union goes, please, Enum. I mean, these people just need to make a decision. Want to store several things? Use you, which is struct. But store just one thing with different possible types? Dude's your man. So basically, union. Store one thing with different. Yeah, that's a union. And struct goes, I'm calling him. Who's him? Union goes, hey, wait. Enum goes, who's he calling, dude? Struct and Union goes, shut up, Enum. Union goes, look, let's not cause any more problems here. And Struct says, hello, can I speak to the Bluetooth service, please? Union says, hey, let's just think about this. Struct says, what do you mean? He'll give me a call back? Union goes, this doesn't seem like a good idea. Struct goes, no, let me leave you a message, my friend. Enum goes, who's on the phone, dude? Struck goes, be quiet, Enum. Can't you see I'm on the phone here? Listen, you just tell him that if he wants to store a float or an int, he just needs to come see me. Or I'm going to come see him. Understand me? Hello? Hello? Union, easy man, just try to keep calm. Struck, on hold? They put me on bleeping hold? Union goes, they what? Pass me the phone. Oh, that man, the Eagles. I hate the Eagles. So you want to pack your field? Is that what you're so fat? Struck, you're entering a world pain, my friend. Okay, that was not a good dialogue. Like, honestly, I didn't get half of it except for the enum part. Like, the reason why enum goes, like, you want, like, hey, where is he saying? Oh, you want me to do what? Want me to do what? Is because when an enum is stored inside a union, that's basically like, not union, a struct, right? And when an enum is stored inside a struct where there's a union inside that enum's purpose most likely is to tell us how the value in the union is stored, like what property, right? And so I don't know. It's just it's very confusing. I shouldn't have read this. Okay. Okay. Next one. Okay. Sometimes you want control at the bit level. Let's say you need a struct that will contain a lot of yes, no values. You could create the struct with a series of shorts or ints. Okay. Create a struct with shorts and ints, and these are like flags. So we have low pass VCF, filter coupler, reverb, sequential. Okay. So each field will use 16 bits, it looks like, but we're only using we're basically only using 1 bit to tell us whether or not things are on or off. It seems like a waste of memory. Okay, it's wasting a lot of memory because it's 2 bytes, 2 bytes, 2 bytes, 2 bytes, and yet we're only using 1 bit per byte, 2 bytes. Huh. Okay. Yeah, so that would work. The problem is that the short fields will take up a lot more space than a single bit that you need for true false values. It's wasteful. That's what I just said. It would be much better if you could create a struct that could hold a sequence of single bits for the values. And that's why bit fields were created. Okay? Sure. Oh, okay, bit field store a custom number of bits. A bit field lets you specify how many bits an individual field will store. Sure. For example, you could write your struct like this. So what's different about this? Oh, okay. Store an unsigned int. Each field should be an unsigned int, but then we have this :1 here. It means that the field will use only 1 bit of storage. Sure. By using bit fields, you can make sure each field takes up only 1 bit. Okay. If you have a sequence of bit fields, the computers can squash them together to save space. If you have 8 single bit fields, the computer can store them in a single byte. Okay, so I think this is like a hint for the compiler to kind of just smash it all together. Okay. Sure. How many bits do I need? Bit fields can be used to store a sequence of true-false values, but they're also used for other short-range values like months of the year. If you want to store a month number in a struct, you know it will have the value of, let's say, 0 to 11. You can store those values in 4 bits. Why? Because 4 bits lets you store 0 to 15, but 3 bits only let you store 0 to 7. Yeah, so you can store 4 bits consecutively to represent a month. Okay. And any other things will just collapse into the same, I guess, data? Address? Okay. So is this your first visit? Okay, so let's say, like, okay, I see this. This problem is going to have us define how many bits we need for our bit field kind of struct. So is this our first visit? We just need 1 here. Will you come again? 1 here. Fingers lost. Well, you can use up to 10 fingers, and that is going to be 4 bits. So 114. Did you lose a child in the shark exhibit? I guess that's 1. And then how many days a week would you visit if you could? That's 3 because 7 days. Something like this. So 11413. Yeah. Okay. Onwards. Why doesn't C support binary literals? Because they take up a lot of space. It's usually more efficient to write hex values. Oh, like representing, like literally, like declaring, for example, like int int x equals like something like this. Oops, what am I doing? Like that, and interpreting that as straight up binary. Yeah, no, that takes up space. Space as in like, I think, code space. Why do I need 4 bits to store value up to 10? 4 bits can store from 0 to 1111, which is 15, but 3 bits can only store values up to binary 111, which is 7. Okay. So what if I tried to put the value 9 into a 3-bit field? The computer will store a value of 1 in it because 9 is 1001 in binary, so the computer transfers 001 instead, so it truncates. Are bit fields really just used to save space? No, they're important if you need to read low-level binary information. Okay. Okay. Such as if you're reading or writing some sort of custom binary file. Sure. Okay, so bullet points. A union allows you to store different types of data in the same memory location. Very important. So, you can only, if you have a union, you can only store or use one of those properties. And you have to be able to recognize which one you stored before so you can access it later. Otherwise, you're going to be pulling the wrong value when you access the union property again. A designated initializer sets a field value by name. Designated initializers are part of the C99 standard. They are not supported in C++. Oh, that's interesting. Oops, what did I do? Oh, this is totally not where it stopped. Uh-oh. Okay, I think I know what they're saying. So with this one, this designated initializer thing we did here, this is actually only after C99, not the original like C89 or something like that. So okay, if you declare a union with a value in braces, it will store it will be stored with the type of the first field. Okay, the compiler will let you store one field in a union and read a completely different field. But be careful, this can cause bugs. Enum stores symbols. Bit fields allow you to store a field with a custom number of bits, and bit field should be declared as an unsigned int. Cool. All right, so we finished another chapter. We're gonna get commit. We're moving much faster now, huh? Structs and unions. How's that? Okay. I think next one, let's take a pause and go back to Webby and see what we can do with like structs and unions in there. And then we can transition back here with some data structures and dynamic memory. I think in here we're going to go through like linked lists and things like how to actually use memory in the heap and so on. So it'll be fun. This is starting to, we're going to start to be able to make really, really useful stuff. So, all right, talk to you next time.